Hello everyone, welcome to the second lecture of sixth week of Scalable Data Science Data Mining course. Okay. So we were discussing, if you remember, we were discussing the problem of frequent count, okay, where the idea is that you are given a stream, okay, this is the stream processor and you have a stream A, B, C, A, D, B, so on and so forth. Okay, so and then you need to estimate the counts of most frequent items. Okay, so we are still so counts of most frequent items. Okay, and we kind of we discussed, we didn't show formally, but we I mean you can think that you cannot guarantee that you will have counts of all items, okay, or even that you can have counts of most frequent items, but exactly, okay, using sublinear space. So we are trying to do this using sublinear space, okay. uh, that is space which is, suppose you have seen m items, we are trying to do this such that the space is sort of not dependent on this m exactly, okay. uh, and we saw that basically frequent here kind of means item x such that f of x is greater than epsilon m, okay. uh, and we want all frequent so till now we got the sketch where all frequent items were introduced, or were identified, but some extra could also be potentially identified, okay. uh, and also we sort of can get their count within the, so if fx is the count, we can kind of get that within plus minus epsilon n. So so you can say fx plus minus epsilon n. Okay. So this range, so f hat x will be in this range. Okay. And in order to do this, we have uh, used what is called a counter based. So we have seen two algorithms, but both are counter based. That is, you maintain big O of 1 by epsilon many counters, okay, and you try to get it, okay. Now, today we will see first, okay, uh, a sketch paste, and sketch paste, as we discussed, basically means that for every item x, okay, we will map it to uh, like let's say a d-dimensional hash, okay. So we will have a hash function which maps it to this cell, okay, 1 to d, okay. And then uh, we sort of uh, have w many such items, okay. So we we have hashes, w many hash functions, and we have w many such items. So the way we think about it is that each of x is basically mapped to a w dimensional vector. Okay, so this is 1 to w. Okay, and then we do some computation on these vectors. Okay, some linear computations on these vectors. Okay, so sort of the broad idea here is that item gets represented into a w dimensional vector. Okay, and then we do some linear computation here to sort of store the count. Okay. Uh, okay. So let us get into the detail of how this is done. And the sketch we will be discussing today is called the count min sketch. It is a very simple sketch, and we will see some simple generalizations also. Okay, but it's a simple sketch, but it has many good properties, and we will see. We will compare. Okay. Okay, so uh, like we mentioned, so the idea is that model the input stream, okay, as a vector over yeah. So let's say your u is your universe, right? So your kind of x belongs to u. Okay, so your items are taken from this universe u. Okay, and then basically you need to map these hash functions from u to sort of 1 to d. Okay, uh, okay, so you are modeling your input stream as a vector over the items. Okay, and fx, okay, fx is the count. Okay, uh, which in this case you are trying to maintain an estimate. Fx is the true count, but you are trying to maintain an estimate which is f of x is the entry, okay, for dimension x. Okay, so here so basically remember each item is being mapped uh, to one of the d dimensions. Okay, and we are kind of trying to determine we will see how we are trying to determine f of x here. Okay, okay. Yeah, so so furthermore the hash creates a summary. Okay, this summary as we discussed is this w times d. Okay, and you have w hash functions. Okay, you have w hash functions. So here are your w hash functions. Okay, and you have d buckets. So this is hashes, and this is buckets. Okay, so each hash function h. Okay, so let's call this hi, ith hash function. Okay, whenever it gets an element x, generates a number between 1 to d. Okay, and so you get a cell here. Okay, so for each element you get a cell in this whole array. Okay, but you can do this for all w hash functions. Okay, so you get one element in each row. Okay, so for each element x you will get one cell in each row. Okay, and then you sort of you think so each of these cells is a counter. Okay, each of these cells is a counter which is initialized to 0. Okay, So here, unlike the item based sketches, you don't store the item at all. Okay. Instead, you represent the item using these cells in this matrix. Okay. So this item X has got this, and this cell. Okay. Uh, Similarly, another item Y may have this, 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 and this cell. Okay. So every item is kind of represented, you can think, as a W dimensional vector. Okay. But there can also be collisions. Okay. So the collisions will not be the same, but there can be some collisions. Okay. Uh, okay. So this is the setting. Okay. So this is your sketch. Okay. And every counter here, okay, is trying to store the uh, f of x. So for example, this is trying to store f of x. This is trying to store f of x. This is trying to store f of x. And this is trying to store f of x. Okay. And similarly, the counters corresponding to y are trying to store f of y. Okay. So this would have been all right if there was no collision. Okay? But we will see what happens when there are collisions. Okay. So what is your sketch? Okay. So your sketch, as I said, is that you initialize this AWD to 0. Okay. So this matrix is called A. Okay. So we will call this the A matrix. Okay. Or the sketch matrix. Okay. So you randomly choose W hash functions. Okay. These should be uniform random hash functions. Okay. And then you sort of choose like this matrix, okay, which you initialize to 0. So all the counters are initially 0. Now we are processing here an item X along with its count. Okay, so X is the item and C is its count. Okay. Now for each item and count, okay, by the way, here we are still in the arrival only model. Okay, we are still in the arrival only model. So this count is strictly positive. Okay. So we will analyze. So this works when the count is strictly positive. Okay. Now you pick each hash function I, each of the W hash functions, okay, in 1 to W. Okay. And then you update the cell H, so A of I and Hi of X. Okay. So remember, the item X corresponds to ith row and then Hith column. Okay, here. Okay, so this is what we are doing. Okay, and then you just increment its count. So you don't do anything else. You just increment the count of this guy. So whatever count is there, you just increment it by C. Okay. Now at the query time, what do? You return the minimum over all I. So again, so this should be Q. Okay. So so at the query time, you are just having an item Q. Okay. So again, for each I, okay, again I belonging to 1 to W. Okay. You look at the entry that is stored in AI Hi of Q. Okay, so that is again you see W many entries in the cell, one corresponding to each row. So there will be some numbers here, right? So each of these AI is trying to store f of q. Okay, you just return the minimum of these. Okay, so this is what it is. So let us just look at the sort of how the algorithm works. Okay, so here are the two hash functions, okay, h1 and h2. Okay, and this is basically the mapping. So the colors correspond to items. So there are 4 items here. So your universe is sort of 4 here. Okay, and blue maps to 2 1. Okay, uh, blue maps to 2 in the first hash function and 1 in the second hash function. Okay, and h1 maps to you know uh, 1 in the first hash function and 2 in the second hash function. uh, this color, okay, this maps to 1. So you see there is a collision here. Okay, but this is not colliding. Okay, so there is a collision in the first dimension. Okay? And then again there is a collision here. So in the second hash function has a collision between orange and turquoise, and the first hash function has a collision between orange and your red. Okay, so let us see how things are estimated. So first you have red. Okay, count is 1. Okay, so h1 is 2, so we add here 1 mark. Okay, and h2 is 1, so we add 1 mark here. Okay, so there are basically in this case your w is 2, your d is 3. Okay, so this is how your thing looks. Okay, sorry, let me erase this. This is red, right? So you have to mark 1 here and 1 here. Okay, then you mark 1 here and 1 here because it's blue. Then again it's red, so you mark these guys, 2 reds in a row. Okay, then 1 turquoise. Okay, so you mark 3 and 2. Okay, okay, yeah, so you mark 3 and 2. Okay, then again blue. Okay, so you mark 2 and 1. Yeah, 2 and 1, right? You mark 2 and 1, and then again red. Okay, and then again sort of red. Okay, again blue. Okay, again turquoise. So you mark turquoise like this, 3 and 1. Sorry, 3 and 2. And then you mark here 1 and 2. Okay, so h1 is 1, so you mark 1 here, and h2 is 2, so you mark 1 here. So this orange is really clashing, so it is just increasing the counts. Okay, and then again you mark blue, which is 2 and 1. Blue is 2 and 1. Okay, now if you query, you see this is so blue maps to 2 and 1. Okay, so for blue, okay, query is going to give you 4. Okay, minimum of 4 and 4, so 4. Okay, if you want to get orange, okay, orange is 1 and 2, so 1 and 2, so minimum of 6 and 3, 3. Okay, so let me also write the actual counts here. Blue is actually 4. Okay, orange is actually just 1. Okay. Red 1 and 3, 1 and 3. So 5, red is 5. Okay. And turquoise is 3 and 2. So 3. So turquoise is 2. Okay. And these are actual counts. Okay. So this is how the algorithm works. Okay. So you see orange is being overestimated because what is happening is both of its coordinates have some collision. Okay. But even if one coordinate doesn't have any collision, then there is no overestimation. Okay. Okay. So now, yeah. So you are sort of uh, getting so you need space of w times t because you want to maintain this matrix. Okay. Times log n because each each item needs, so each is a counter. So remember this is uh, much, or yeah, we will see this is much larger than the space required by the previous sketches. Okay. Which were sort of counter based. Okay. So now additionally, okay, uh, okay, so update time is w. Remember, every time you do an update, okay, you check all the w entries. Okay, all the you have to basically compute the w hash functions. Okay, so update times is big O of w. Okay, yeah, and each item we already saw this, that each item is mapped to one bucket per row. Yeah. Okay. Okay. So what kind of guarantees can we provide? Okay. So we are interested in, if you remember, epsilon delta type guarantees. Okay. So what is this epsilon delta type guarantee? So we want, so suppose your fx hat is what you are returning. Okay. Then, okay. So then we want guarantees of this form. Okay. That, and suppose fx, yeah, is the true sort of true estimate, okay, of f. So we want guarantees of the form, this should be between 1 minus fx to 1 plus epsilon fx. Okay. Now we will see this, but actually you don't need this. Okay, or rather you don't need this. Okay, so your lower guarantee is actually fx. Okay, so it is going to estimate at least f of x. Okay. Okay, but it may do some overestimation. Okay, you can see why, right? So every time, okay, yeah, so every time, okay, you sort of you look at the matrix and you look at all the cells where x is being mapped. Okay, every time all the cells are getting updated when x is there. Okay, so no doubt all arrivals or x of x are being counted. Only due to collision some extra arrivals may be counted, but for x all arrivals are counted. So this is something like the space saving guarantee. Okay, that you are never going to underestimate the frequency of x. Okay, so on the lower bound there is no epsilon actually. Okay, So the question is, can we show something like this? Okay. And here, uh, we will see what can we show here. Okay. So this part we will see next. Okay. Okay. So in order to get this kind of, and this should hold with probability 1 minus delta. Okay, so this guarantee, whatever guarantee we get here, should hold with probability 1 minus delta. Okay, so suppose we want this kind of a guarantee, then what we do, we design the sketch like this. Okay, we have this d. Okay, d is the number of buckets as 1 by epsilon, 2 by epsilon. Okay, so twice 1 by epsilon, but this is ordered 1 by epsilon. Okay, so you see, so this is similar to the space requirement in terms of the d dimension, is similar to what our counter based sketches were asking for. They were asking for, remember, k is equal to 1 by epsilon many counters. So here we are saying at least each this many buckets per hash function. Okay, but additionally we have this w dimension, which we should take as uh, at least log 1 by delta. Okay, now this is typically a smaller number. So if you take epsilon and delta to be same, so epsilon and delta should both be very small. So something like 10 to the power minus 2, let's say 10 to the power minus 2. Okay, if you want with 99% probability, it should be within 0.1 1% of the actual value. Okay, then you should take it like this. Okay, and then this is going to be 100, but this is just going to be log 1 by 100. Log 1 by 100 is very less, is sorry, this is log 100, not log 1 by 100. This is log 100. Okay, and log 100 is, if we take to the base 10, then it is just 2. To the base 2 will be slightly higher. Okay, but smaller than 100 itself. Okay, and much smaller in fact. Okay, okay. So so suppose we have taken the buckets like this, the design the filter like this, then suppose y1 till yw, okay, be the w estimates over which we are taking this minimum. Okay, so first we are going to analyze this yi. So remember, we are getting for each x, we are getting w counters. Okay, so we are kind of, each of them is at least supposed to predict f of x. So we are getting like these w estimates of f of x, and we want to first, and then we are, what we are returning at the end of it is minimum over this. Okay, so so that is fine. Okay, uh, uh, but first we want to see, suppose we did not, return minimum over this. Okay, but just what kind of bounds can we give on yi themselves? Okay, how are yi's bound? Okay, and here we are going to do, as we know, all of these are lower bounded by f of x, so lower bound is tight. Okay, so we only need to analyze this upper bound. Okay, so in order to analyze, we calculate the expectation of yi. Now this yi is random. Okay, it's random because of the randomness in the hash function. Okay, so what is the expected value of yi? Okay, now you are looking at basically the cell hi of y, right? Or rather, sorry, yi is basically the count of x, right? So yi, so you are looking at the cell hi of x. Okay, so you are looking at the cell hi of x. Okay. Now consider all elements y such that hi of y, okay, is actually equal to hi of x. Okay, so basically what we are looking at here is, suppose we are looking at the ith row here and x is mapping to this cell. Okay, so we are looking at all y's which are mapping to this cell. Okay, okay, and we are seeing their count. Okay, so yi is going to be just this, right? So here the expectation is over which guy is mapped to this. Okay, but basically your once it maps, it's going to count the frequency of that particular y also. Okay, okay. So this sum is the count. Okay, and what is this? So x is always going to be there. Okay, now what is the chance that any particular y is going to be mapped to uh, this x? Okay, the chance that any particular y is going to be mapped to x is 1 by d, because there are d buckets. Okay, so probability that y gets, or let me put it this way, that probability that hi of y is equal to hi of x is 1 by d, which is nothing but epsilon by 2. Okay, and if you just add all the counts, so if you just do summation over y, f of y, this is m. Okay, if you subtract just the count of x, because you have already taken into account f of x, this is x such that y not equal to x, then this is this minus f of x. Okay, and epsilon by 2 fraction of these is going to be counted on an average. Okay, because the probability that y is going to be mapped to x, hi of x, is epsilon by 2. Okay, so this extra count is going to be epsilon by 2 times m minus f of x. So you have the f of x all the time, and then you have with probability epsilon by 2 m minus f of x. Okay, so this is your expected value of yi. Okay, now we can do Markov inequality, our favorite Markov inequality. So remember that Markov inequality says that for any positive random variable y, okay, okay, the probability that y is greater than a, okay, is less than or equal to expectation of y by a. Okay, and so we want to look at the random variable yi minus f of x. Okay, and we want to see what is the chance that this random variable exceeds epsilon m. So remember earlier I was saying that we need sort of a guarantee of this form, that 1 plus epsilon f of x. Instead, the guarantee that we are really looking for is uh, f of x plus epsilon m. Okay, so we don't want this to exceed f of x plus epsilon m. Okay, uh, yeah. So this is the event that we are looking for. But you remember that we are only looking for frequent items. So items with true count greater than epsilon m. Okay, so then we sort of have also a guarantee in terms of uh, you know this, because if f of x is greater than epsilon m, so this is something like epsilon square m. Okay. Okay. So epsilon square f of x. Okay. So this term is something like at least epsilon square f of x. You see here. So okay. So this is the event that we are interested in, and now this, as we have already seen, is a positive random variable. Okay, because we never underestimate, so it's either 0 or positive. Okay, non-negative random variable. So, and we can use the Markov inequality, and this is a straightforward application of Markov inequality. So epsilon by 2 m minus f of x is your sort of your expectation of y, and epsilon m is the a. Okay, so it becomes this, and then if you ignore this part, f of x compared to m, okay, uh, you get a loser upper bound basically of half. Okay, epsilon m cancel, so this probability is definitely less than half. Okay, in fact, if one can think that this is strictly less than half, because this f of x is not 0. If f of x is 0, then we are already not doing this analysis, so this is strictly less than half. Okay. Okay, so uh, okay, so this holds true for all yi. Okay, so this probability bound holds true for all yi. Okay, okay. So now remember what we are returning. Okay, we are returning the minimum of yi. Okay, so we are actually returning the minimum of yi. Okay, this is what we are returning. Okay, is your f of x hat. Okay, and now we are looking at the probability that what is the chance that f of x hat minus f of x exceeds epsilon n. Okay, this is the event that we are looking at. Okay, and this would be if all yi exceed epsilon n. Okay, now we know that probability that I'm sorry, yi minus f of x. Okay, all yi minus f of x exceed epsilon n, and we know that probability that yi minus f of x exceeds epsilon m, okay, is less than or equal to half. So what is the chance that all of them will exceed f of x? Okay, less than or equal to. So the probability of sorry, so the probability of this whole event happening is less than, actually strictly less than, half to the power, uh, in this case your w, okay, which is log 1 by delta. Okay, so this is going to be 1 by 2 to the power log 1 by delta, or 2 to the power minus log 1 by delta. Okay, and this is 2 to the power, so if you put the minus inside, okay, 2 to the power log delta, which is less than or equal to delta. Okay, so we have shown that with probability 1 minus delta, okay, we can answer the query within this bound. Okay, but we are basically taking, okay, so let us see, yeah, so we are basically taking a space for of actually uh, 1 by epsilon log 1 by delta. Okay, so earlier we were taking a space of 1 by epsilon. Now we are taking a space of 1 by epsilon log 1 by delta for getting this count. Okay, We don't get this kind of bound with high probability just by using 1 by epsilon variance. Okay, but yeah. Another thing is earlier, remember, the counter-based algorithms were all non-randomized. Okay, this is a randomized algorithm, and where is the randomness? The randomness is in the hash functions. Okay, so the hash functions are what is making this algorithm random. Okay, hence we have, so sometimes with a small probability delta, okay, we will violate these bounds. Okay, the other side we will never violate. Okay, but we may exceed epsilon m with a very small probability delta. Okay, but in the non-randomized case we will never exceed epsilon. Okay, so kind of like a war sketch, you if you think like that, but we will see why this is better. Okay, uh, yeah. Okay, so and again, so this is also covered in uh, sorry, this lecture notes of Amit Chakravarti. Okay, but for the count sketch also you can look at these survey by Graham Cormode. Okay, so Graham Cormode is also so it's a very good exposure, and he also has some slides here.